Okay, here is the team. We have another paper, a bit about similar idea that is going to be presented at the AA conference. This one is at the Cognitive conference. And actually here I'm the only author because I'm the coordinator of this project. In the first part of this presentation, I'll try to persuade you that I'm a serious person and that we are at a serious department. Because in the second part, it will be a little bit strange, okay? So briefly, we come from the Josef Stefan Institute, which is an institution with 1,000 researchers. Probably we do some good stuff, and according to some statistics, we are. And the Department of Intelligent Systems has about 35 staff. And we try to do lots of interesting things. Here you see actually there are 3 groups in our department: ambient intelligence, agent and multi-agent systems, and computational intelligence. We have also language technologies and so forth. These are the prototypes. So for example, you can buy elderly support smartwatch with 16 functions. You can actually buy it now. And for example, you have the heart failure system, which is also very advanced. For example, in one of the options, you can listen to the heart and prognose whether it's working well or not. You have decision models. And there are basically around 30 systems. Some of them are actually commercial prototypes actually being sold, and the other are research prototypes. But many of them show they actually exhibit some properties which are more advanced than the existing systems, either commercial or research systems. And we have also won a couple of world championships and also made some very good publications. So we are serious, okay? To a point. So what we do in the previous slides is about 95% of our time. There is maybe a couple of percent of at least my time that I devote to a little bit strange activity. I try to care about civilization, human civilization, European civilization, and Slovenian civilization. So this is one of the goals I try to do. Let me give an example. In regards to the superintelligence or intelligence, artificial intelligence has the power of nuclear bombs. So it has to be somehow regulated. And for decades or so, we are trying in a global movement, we are trying to put that into legislation of United Nations, European Parliament, Slovenian Parliament, and so forth. And in September, so just 1 month before, European Parliament accepted, you can read there, accepted a resolution calling for a ban on killing robots. So yeah, we did it. And also I'd like to appeal to the Cognitive Science Society to formally fill, everything is arranged, you just have to fill the form, and then you will be accepted as well. Okay, now we move on. And this is the second part of our story. Can we somehow estimate, can we calculate what is the number of civilizations in our galaxy? And furthermore, can we estimate the longevity of human civilization? So how long will we, as human civilization, persist? Nothing is eternal, so we know there's some time limit. Can we somehow calculate or estimate this time limit? So this is the second part of the story. That's why I have to introduce you first through the technical point of view. There is a well-known Fermi paradox and also a well-known Drake equation. Fermi paradox is pretty simple, so I guess we will all understand it, right? Fermi was a famous physicist. He was working on the atomic bomb. He died in 1954. So he developed his theorem. Where is everybody? So he developed this paradox or theorem before that in the 50s. And according to probabilities, there should be some other civilizations, and we should have the contact with them already. But see, it happened in 1950 and something, and still we don't have any contact with other civilizations. How is that possible? And Fermi was very good at calculating these probabilities. So he was one of the best brains in that particular category. And he calculated and said that there should be somewhere here. We should have some contact, and still we don't have it still now. The Drake equation is a little bit more complicated. So if you, to a point, understand it, it's very good. So maybe you understand the basic idea. The basic idea is that you put the number of technologically advanced civilizations in the Milky Way galaxy, so it's our galaxy, in a form of an equation. Okay? This equation is roughly like this. So this is the number of planets. This is the number of planets, but you have to multiply the rate of formation of stars in the galaxy with the time span of our galaxy. So there is time span of our galaxy multiplied here, and it's divided here, okay? Divided here. And then you get some meaning, because if you read it like this, you might have some problems at the beginning. So this is the number of planets, the number of planets with an environment suitable for life, the number of planets where life, just life, actually appears, when there is intelligent life, and there is civilization. But there is time span. We don't know how much a civilization on average lasts, and this is L. So this is L, please remember L, and please remember N. Okay, so these are the two numbers we are interested in. The number of advanced civilization in the Milky Way, and the length of time, the length of time span. Suppose we calculate and it turns out it's 10 years. What will happen then? Then our calculations are wrong, probably, right? But suppose it happened to be 10,000 years, like the Drake proposed, or 1,000 years, or 100 years. And I will try to show you what we get from our computations. There is a guy that recently published, it's Sandberg and colleagues, and they published a little bit difficult to understand their model or approach. Instead of, I need to go back. If you look at the numbers here, what previously the researchers did was put some numbers here. For example, what's the fraction of suitable planets? It's P, probability, even though it's FL or FI or whatever, it's actually probability, so between 0 and 1. And they put numbers, for example, 0.001. They said, oh, this is the best estimate we can think of as the best physicists or chemists or whatever. So they have put exact numbers here inside. And of course, then this is just a simple computation. But what if instead of 1 P probability, here we put a probability distribution? Now, all of you that haven't heard about that probability distribution will likely not understand much of the rest of my presentation, unfortunately. But I will try to also explain you what actually is going on. And those of you that have studied the probability distributions, I would be very happy if you understand the whole story. Okay? Okay. But even you don't understand exact mathematics, probably you can understand at least the general idea. So instead of one number here, we have a span of numbers. For example, instead of 0.1, you have a 0.1 to 0.1. So we have some interval of possible numbers. And not only that, we have some distribution of these numbers. They can be uniform, or they can be in different ways. Okay? And Sandberg studied that and proposed the following. So these are his numbers here in his distribution. For example, log uniform. Log uniform means just logarithmic. You apply a logarithmic on the uniform, and then you get a little different curve. Maybe you read a little bit about this, and maybe you pose a question or two, since there is some time. Okay, any question? Anybody understands anything from this?
Maybe you should explain what is a normal probability distribution, or
okay.
Distribution, and then
Normal probability distribution, so that all numbers are equally probable. Okay? For example, I have three numbers, 0.1, 0.2, 0.3. Okay? And their probability is equal. So the probability of that number is equal. And I have this continuous interval, not just three numbers. I have a continuous interval, and all those numbers, all the probability of those probabilities are equal. And then I apply a logarithm on that. Okay? And I apply a logarithm on that, and I get a different curve. But it's just a logarithm. You know the logarithm, how the logarithm looks like. Right? Mm-hmm. Some of them are a little bit more complicated, and to be fair, a group of students, they were working on this for months, and maybe 2 months, something like that, just to reproduce the results, because we just couldn't reproduce the results. It's a bit, the principle is easy, you know. If you take a look, oh, just a simple mathematics, but when you try to do that, and of course you must make a lot of simulations. There's a huge number of simulation runs, because each parameter is not just one number, it's a whole span of numbers. But you get the idea, right? We can follow, we can continue, right? Because now you're going to see how long you're going to live as human, no, not as person. Okay. So this is Sandberg's computation. I studied this for months, so you don't have really a good chance to understand it here in 1 minute. I'm trying to be positive, not to discourage you. But actually, you see, this is n. This is n, number of galaxies. So it's not actually n. It's not the lifespan of human civilization, but it's the number of galaxies. And this blue line here is probability distribution of n, number of galaxies. Where is 1? Where is number 1? 1, 0, 0. Anybody?
I think at the top of the blue.
Somewhere here, right?
Yeah, at the start of
Because 10 on 0,
How can there be less than one
it's
galaxy?
logarithmic.
Yeah, but how can there be less than one galaxy? We already know that there's at least one galaxy. We're in it.
Very good point. Bravo, bravo. Because they have just tried to put probabilities inside. That was the first error they did, or error. For example, we think we have a couple of ideas how to improve their computation mechanism. Okay? And one of them is exactly what you said, so it's a brilliant remark. But actually, it can be 0, because at some point, there might be 0 civilization in our galaxy. Then, for example, if the time span is short, for example, 100 years, one intelligent civilization appears here, disappears here, disappears here, and in a particular time it can be 0. Okay? Because this shows you what is at some particular time, for example now, and it might be only the chance that we are now here, and it won't be here for the next 1,000 years, something like that. Okay? But anyway, we think this is one of these possibilities of improvement, and we're going to talk about it later. Okay, so you see this? It's not 0 here, and then it goes up, but actually goes to 10 or 9. 10 or 9 is a pretty big number. It's a kind of billion, right? It's a pretty big number. But you must have in mind that you should extend this. But if you extend this, then what you get is it gets low pretty fast. So here it is basically 0. But just through this logarithmic presentation, it's difficult to present it in a linear scale. So here, you extend that to 10 or 9, and this is, of course, like this. And you see that from here, it's more or less 0, right? Computer and mathematical scientists can probably see that. But still, it is kind of this form. So somewhere around 1, you get a hill, and then it goes down pretty fast. What is this red one? This red one is an integration of the probability density, and what does it mean? if I integrate, anybody integrates probability density, you get what? Computer scientists, mathematicians. Mathematicians. What do we get? Probability, right? So here is number 1, and this red shows us the probability that there is at least one civilization in our galaxy. So it is something like here, because one is somewhere here, right? And it is about 50% chance. It is about 50% chance, according to Sandberg, that we are currently alone in our galaxy. So it's pretty amazing. People are still discussing about this, whether, of course, there is lots of media, is it possible or is not. This equation is a bit not exact, not really exact, because you have so many parameters, you don't know if it has set all the parameters right. But it might be. It might be that this result is not totally wrong. So these are our results. The problem with our results is that we would like to publish them in an SCI paper, and therefore we cannot publish it here, because otherwise we cannot publish the paper in some SCI journal. But you get some fancy stuff like this, and I can present you the general idea. So this is n. So this is the number of civilizations in our galaxy, and you see it goes to 200. Sorry. Oh, so it's pretty high. So 20,000 here, right? And 100,000 here. And here is the logarithm of the maximum span of longevity of civilization. And you see that it looks like, so this is again logarithmic, and it is kind of deceiving that you see the red hill there. But obviously you see it's somehow, most of it is here, but it's not most of it is there. That's the wrong impression because of the logarithmic scale. Can you see that? Anybody? I told you it's a bit complicated. We were studying such graphs for a week or something like that, discussing whether we see it correct or we don't see it correct. What about these ones? This one is logarithm of n, okay? It again goes from, at 0 it is 1. At 0 it is 1, and at 15 it is a bit high again. And here you have the same story, and here you have the logarithmic scale again. Now, if you try to put it into a linear scale, you need, for example, 5 or 10 graphs to show you this. But then you can actually see what's going on. Unfortunately, if you want to show the whole story, then you have to use some logarithmic scale. Otherwise, you cannot present what's going on in this span all along. Anybody still following? Yeah. Okay, that's done. So what do you see here? What do you see here? Does anybody see here anything? How long are we going to live? Are we going to live for 100 years? Are we going to live for 10 million years? What do you say? I thought so that nobody is going to be able to do that because we needed for that, for example, at least a couple of days studying and thinking about it. But maybe take a look at this one. So it is close to 1. And here it is 10 on 5, okay? And here it is, for example, 10 on 2. So 10 on 2 is 100, right? 10 on 2 is 100. So between 0 and 100, it seems to be that most of the thing is going on. So it seems to be that there is no huge number of intelligent, technologically advanced civilization in our galaxy. So previous assumptions do not seem to be confirmed by these new computations. And why did they do it in that way? For example, the Drake. Drake was thinking about 10,000 civilizations and a lifespan of about 10,000. So these numbers were the same, n and l were the same, and they were about 10,000. So in our calculation, and Sandberg's calculation, based on on the improvement of the sample calculations, we don't get such big numbers here. So this is pretty low here, see? And most of it is here. And again, this is logarithmic, so there it is much, much lower than what you see here. So the bulk is here. The bulk is here. And there it is much lower there. So what can you conclude for this picture? For example, what is your conclusion? Well, I can just present you my opinion. This is still an ongoing research. But it seems that there are two options. One is here, and the other is there. The two options are as following. Lifespan of a civilization, advanced civilization like ours, is kind of limited. We don't know exactly the number, but it seems to be pretty limited. How long is that? It's hard to say. It's 1,000 years or 10,000 years. Hard to say exactly. But it seems to be pretty limited. And it seems that civilization pop up here and there and here and there in this computational model. Okay? They pop up here and there and here and there, and then they destroy each other or whatever. But we don't know exactly what happens. Maybe it's global warming, maybe it's nuclear war, maybe it's AI. But it can't be AI because AI would still communicate with the rest of the society. So that one doesn't seem to be very relevant for the story. And what's in the other end? In the other end, you have a lifespan of civilizations that takes a long time, billions of years, maybe, or at least millions of years. But then these civilizations are very, very, very special. Okay? They appear very, 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 under very, very strange circumstances. And it's not exactly clear why are these on Earth, where are these very, 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 very special circumstances? Because it seems that our planet is pretty much similar to several other planets. There have been some papers that our planet is very, 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 I would need to say 1,000 times special. There are some publications. But I'm not sure if that is the case. Whatever, you see that clearly there are two options. And somehow they thought about it before. What we did was we did an advanced computational model, which we think is the best so far. It is still a work in progress. And briefly saying, it's based on AI methods. So what we are good at is AI methods. And first we did something in relation to the Laplace theorem, to the Boyan-Cesnik, if you're familiar with his dealing with the naive Bayes improvement over the number 0 or very close to 0. And that was already presented there. But there are some other methods. We can use machine learning methods. That is our plan for the next month. And we can also use deep neural networks. If nothing, it's a kind of modern buzz, and you can buzzword, so you can try it and see what happens. But it seems to be that these two options are somehow emerging up. So these two options I mentioned to you before, and nobody knows which one is the correct one. Nobody knows. Maybe human civilization will last for long, but there is pretty, let's say, around 50% chance that we won't last very long. So you will last for a short time. And what does it mean then? Was it in this case? Okay, I told you it's a work in progress. It's improvement of our best computational models. And then maybe we should shift our civilization priorities. Maybe we should not think about buying best shoes tomorrow, but maybe as humans we should think about sending, I don't know, rockets to Mars and so forth, onto the other stars. So this is the question. I asked this rhetorically, hypothetically. But what is fascinating is that these models are getting better and better. Each year they're getting better, and they are telling us something. There is a story, in my opinion, in this area, and hopefully scientists and politicians will try to figure out how to react. Okay, thank you very much.
So questions? Well, I have a question. So from these models, if we want to find out our fate as a human never say if they're right. Because if we say that they're right, we will be dead. You know? We can never know if the model will be correct in saying we will live for 100 years. Because in 100 years we will die, and we won't be able to say, yeah, this was right.
The way of dying is a little bit unclear.
Yeah, no, but actually my question is how do we know that the models are getting better? What is the process of, how do we distinguish one model from another in terms of their quality in this kind of models?
Well, what we did, what we improved over the Sandberg, and what Sandberg improved over the older models is as follows. Sandberg introduced probability distribution over just probabilities. And we introduced AI modifications or AI methods on top of the Sandberg approach. The second question, actually the first question was about how are we going to die? I don't know.
Well, not how are you.
I hope I will never know that, because it will still be okay when I go to heaven. Okay.
But
yeah, nothing.
no, the correctness of these models, well, let's hope that they're never correct in actually specifying a number, because we want to live forever. Or
Nothing lives forever, so that's kind of not realistic. Everything die. Everything die. Humans will die as well. So the question is, how are we going to live till then, and how is this transformation going to happen? For example, humans can appear to a new type of humans. For example, our civilization can emerge to or progress to some other civilizations, but as human civilization, it's only a matter of time, and we probably are aware of that. And it's maybe interesting to say that we have just n and l there, but actually there are about 9 parameters. So it should be a 9-dimensional picture here, but it's a bit complicated to look in 9 dimensions. Okay, we are trying to do some experiments in higher dimensions and so forth. And it's a search going on. It's a search going on, and if anybody is interested, you can join this research. Yeah, but you're sure nobody knows for exact what's happening, and nobody knows what's going to happen. But what you will probably realize is, for example, if a nuclear war starts, it won't immediately demolish all the human civilization. You will be able to see at least that for a while. Or if our civilization starts to degrade slowly, for example, saturated, you will be able to notice that. And unfortunately, if you notice that decay, you will probably notice that you're already in that area. And for example, if you look at this world growth, there are some projections that the world growth won't continue, so that in the future decades, there are some estimates that the world civilization will go down. But for the moment, we are definitely growing up. Each year we are stronger, we are better. And for example, some aliens attacked us this year, or 10 years before, or 10,000 years before. When we are strongest to defend? This is a hypothetical question. Now, each year we are stronger, we are better. However you look at this is the case. So obviously, in different ways, you can see that the human civilization is progressing fast and strong. And we are actually progressing faster and faster. So this is fascinating. The progress is not being stable or being saturated. The progress is speeding up. And most likely we will see the singularity point where we will actually jump to another civilization. And this is another kind of way, because if we know better, then we will react better. Okay? This is you have to see this as a positive way. Suppose you're in Titanic, and you're going to hit something, right? You're going to hit it. It's going to be bad. You don't know about that. Of course, then you will hit it. But if you know what's going on, you can maybe prevent it. Titanic would be easy to prevent. Lots of the solutions are possible. But people didn't know about this. Sorry about that. Now we're trying to decipher this, and with some luck we do that. And we will know how to react. And we will react in this way. So I think this is a very positive way. As human civilization is maybe going through some problems, we can try to estimate that, and then we try to persuade politicians which will be a little bit difficult because nobody, now you are very smart people here, but I'm not sure that you understand it all, and that the problem with politicians is going to be probably much harder. Yeah, first.
I would like to return to the first Drake equation, to the suppositions that are put in. That FC, technology that releases detectable science.
Signals.
Signals, yeah.
Yeah.
Is it here suppose that our civilization is in such one of such civilizations?
Yeah.
Are you sure?
We are emitting the signals for around 100 years, and the nearest star is Alpha Centauri. It's about four something light years away from us. So we have reached 50 times further. Our signals have reached 50 times further than the nearest star. The problem is that these signals are not very strong as such. For example, I emit something, this signal gets dispersed, and it's hard to detect in large distances. But there are some signals which have very long penetration rate, and some of them are being submitted deliberately. I think that Russians and some others, they are deliberately sending the signals, we are here, please contact us. Okay? Some say it's dangerous, but actually that's what we're doing.
Nasprotujem temu, skratka, ali smo sposobni sprejeti signal, ki bi ga dala civilizacija enake vrste, kot je naša, za razdalje 100 svetlobnih let.
Ja.
Kolikor vem, ne.
Tu je tudi diskusija in najdemo članke o tem, a to je, a to ni, ampak nisem ne elektrotehnik, pa ne fizik, da bi lahko o tem debatiral. Vem pa, da obstajajo članki, eni trdijo tako in drugi drugače. Ne?
Okay.
Ne vem, če ste opazili, a je v redu, če govorim slovensko? Anybody objects Slovenian language? Če ste opazili, so zdaj namestili oziroma nameščajo nove naprave, s katere naj bi zaznali, ali na teh bližnjih planetih je življenje. Se pravi, to se tudi da zaznati, ampak rabiš specialne naprave in to zdaj en projekt, ki teče, je kar zrak, ampak pač to raziskuje.
Tudi projekt SETI je bil dolga leta, po koncu potem so ga ustavili, pol je bilo neki kako že s prostovoljnimi prispevki naprej gnani in tako naprej. Ampak poglejte, to je obdobje, mogoče nekaj desetletij, da so se s tem ukvarjali, potem smo pa kljub naši silni tehnološki, ne vem koga, superiornosti zadevo ugasnili, kar pomeni, da nismo sposobni detektirati.
SETI še vedno teče naprej,
Ja.
ne? In ravno pred kratkim so analizirali stare podatke in so odkrili čudne vzorce.
Še kakšno vprašanje, last question. No, then thank you for the a bit longer presentation.
Fun.